now back to Just Energy Radio with Dr. Rita Louise.
Hello and welcome back to Just Energy Radio. It's me, Dr. Rita. And don't forget, Just Energy Radio is brought to you by SoulHealer.com and the Institute of Applied Energetics. That's www.appliedergetics.institute.com. This hour, we're going to be speaking with Stephen Manley. I hope you have your thinking caps on because we're going to be talking physics. Okay. Our topic is multiverses, which is really an interesting topic, but then you get into the physics part, and it's like it makes my head spin. But I'm hoping that Stephen can make it like be for a level that I understand, which means you'll understand it, and it'll all be good. Let me tell you a little bit about Stephen, and we're going to get him on the air. Stephen Manley works at high-energy accelerators around the world where his research probes the structure of matter and the forces of nature. He grew up as a free-range college brat in North Carolina. He received an undergraduate degree from Pfeiffer College and a Ph.D. in physics from Columbia University in New York City. After moving up the faculty ranks at Yale University, he moved to the University of Rochester, where he now resides and terrorizes students in the introductory physics course sequence. So please welcome, let me make sure I unmute the right number, to Just Energy Radio, Stephen Manley. Hey, Steve, how are you?
I'm good, Dr. Rita. How are you?
I'm great. Thank you so much for coming on the show. But is Steve or Stephen?
Oh, Steve's fine.
Okay. Steve, we haven't really talked yet, but I have to tell you, I am liking you already. Your book is formatted in an easy-to-read font, and you tell bad jokes. And there is a welcomed absence of vector drawings and mathematical equations. Thank you.
Oh, you're welcome. That's the whole point. Make it a fun thing. You know, the truth is, when I sit in a room with a bunch of physicists, I'm like the slow one. And so I'm always trying to figure this stuff out. So a lot of what this book was about, in fact, was me trying to pull all this together so that it makes sense to me. Because in the end, I figure things out in my own way, and I think I'm actually ahead of some of them because in figuring it out the way that I do, usually I can really get at it. But, you know, when the equations are flying at the board, I'm usually sort of scribbling them down and daydreaming about other things.
I tried to read Amit Goswami's Conscious Universe book. I mean, this was a few years ago, and on an airplane. The only thing I brought to read. Big mistake.
Oh.
You know, and I know we're going to be talking about the half-dead cat later, but I got to that, and I was just like, my head was spinning too much, and I just had to close it. Anyway, so today we're going to be talking about multiverses, and I know I think my listeners have heard that term. I think I have a pretty well-educated group of people that listen to the show. And I know for myself that I've heard of two kind of conflicting definitions, and maybe they're both not multiverses, but I'm throwing this one at you first. But one has to do with parallel realities, and then the other one has to do with separate universes that might be based upon different sets of physics. So when you're talking about multiverses, what are you talking about?
Well, I mean, both of the things you mentioned would actually count potentially as multiverses in the taxonomy that I sort of throw together, the categorization I put together in the book. But the truth is, when I sat down to write the book, that's exactly where I started, because I had really set out to write a book on the convergence of our studies of the very small, which is really what I do, particle physics and study of the nature of forces, and how it has really become tied with our studies of the very large, which is the large-scale structure of the universe, the evolution of the universe, and everything. And I don't know if you're not really familiar with this stuff, it may sound sort of odd that the two would really marry together, but we live in this expanding universe, so if we go backwards in time, the universe was much hotter and denser. So in fact, it turns out that studying phenomena at very high energies, which allows us to use particles to probe to really tiny distances, turns out to be very relevant at the early stages of the universe. So I thought a lot has happened in this area in the last 20, 30 years. It's very exciting. So that was sort of the book I set out to write. And my agent and I were having trouble selling that particular book because I think some of the editors and publishers thought it had been written. I don't think we were trying to sell it right. And he kept saying, gee, you should just write a book about the multiverse. And I sort of kept putting him off. I said, and then he said, you should write a book about the multiverse. And finally, I'm like, oh, okay, I'll look into it. And so I really started looking into the subject of the multiverse, and I became absolutely fascinated by it because the multiverse comes at us from a number of different directions, and I actually found it to be a confusing mess, which is really what led to this book in the first place. It's really a survey of the different multiverse concepts. But to get back to what you asked, the question really that I started with after I pondered all these different ideas for a week was, wait a minute, what do I really mean when I say multiverse or multiple universe? Because after all, a universe, sort of by definition, encompasses all that we know. So how can you even have a multiple universe? And thinking about that, the definition that I came up with for a multiverse is really it is a reality that has portions that are outside of our universe. So then we have to ask, what is our universe? And that's really the starting place. To me, our universe is all that we can actually experience directly in sort of a sciencey way. So it's something that we are causally connected to, which basically means we can touch it, feel it, smell it, build an instrument that can detect something from it, like light or some other particle that's emitted by it. And we have to be connected to it. In other words, light has to have a chance to, from that portion of the great reality, it has to be able to reach us at some point for us to be able to detect it. And then the question, then you ask, okay, well, if that's your definition of a universe, can you imagine things that are outside of that? And you can. In fact, you can in lots of different ways, many of which are inferred from our leading scientific theories, which really is the core of the book. That's the main stuff I talk about. But there are lots of ideas that are out there which are less scientific and which also sort of fit my definition of multiverse. Wow, so there I talked a long time. I think you asked something fairly simple, but I mean that was sort of my starting point, and I don't know which one you want to go or where you want to go from there. But
well, then let me ask this: can we talk about those two different concepts, about the concept of parallel universes, and then we can come back and talk about the concept of multiple universes? I don't know. I think based on separate physics, or that is not the parallel universe idea.
Yeah. Okay. So there are a few. There are a couple. I sort of think of these things as coming from. I guess what you're mentioning, I sort of think of as three different major areas in a sense. The parallel universe idea is generally what people are talking. What they're talking about is something that comes out of quantum mechanics. And this is what I would call the many worlds multiverse. There's a way of interpreting quantum mechanics, and quantum mechanics is this mathematical structure that we have to use when we realize that in fact particles are not like BBs, they're more wave-like in nature, and physicists had to invent a wave mechanics, mathematics that works for waves in order to try to describe particles. And when we did this, the area of physics became known as quantum mechanics. Prior to that, descriptions of phenomena were very much more like particles. So if I threw a ball, for example, if I threw it in a particular direction at a particular angle, I could calculate exactly where it's going to hit on the ground. This is known as Newtonian mechanics. But if this ball were a tiny little particle, then that becomes very problematic, and we can't actually calculate in quantum mechanics exactly what will happen. All we can calculate are probabilities. So there is an infrastructure of mathematics that we use, the quantum mechanics, which we use to understand these types of processes, and we can only calculate probabilities. So there is a way of interpreting this quantum mechanics, because the problem is when an event actually happens, all we can calculate is the probability of all the various things it might do. But then it actually does something. So a way to think about it is a particle decays, and it can decay with two separate orientations, and maybe there's a 50-50 probability of either happening. But when it actually decays, it only does one of them. So all we can calculate is the 50% probability that it'll do one or the other, but we can't actually know exactly which it will do. But in fact, when it does one, I mean, it really does one, and that's what we measure. So the problem is the mathematics seems to collapse instantaneously from a description where both can happen with a 50% probability, which basically is something you have to preserve in the mathematics, to the moment that the event happens, the thing converges into that particular event happening. And this actually leads to causality issues and problems in trying to visualize what's going on. It's as if you have to have instantaneous, faster-than-light transfer of information. So this bothers people. So another way to look at this in quantum mechanics is that every time a quantum mechanical process happens, effectively we have the universe splits into two, and you have one universe where the particle goes one way and another universe where it goes the other way, and these basically proceed with everything overlapping in every other sense, but they basically form two new threads in reality. So in the overall mathematics, we have something which we call the wave function that describes sort of the large scale as the large universe, and all that's really happening in this wave function as this quantum mechanical event happens is that you sort of form two different threads within this overall mathematical structure, and they each proceed. And if you're in one thread, you don't perceive the other thread. So these are sort of like parallel realities where everything starts out to be absolutely identical except for that one little phenomenon. And then they sort of continue to evolve, and they may evolve differently. So this is what people usually mean when they call parallel realities. This sort of out of quantum mechanics. Then there are other ideas.
Let me ask a question in here. I mean, thank you for not using, and I always call it the half-dead cat. You know, so many physicists throw in, you take a cat and you put it in a box, and then you put poison in there, and you don't know if the cat's going to die. Yeah. And it's like, hello, the cat's dead. Okay, I don't know how any probability is going to be around the cat not being dead on the other end. You know, I could never wrap my mind around that. So thank you for explaining it in a way that didn't have a half-dead cat.
Well,
anyway.
Yeah, okay. Well, it's in the book. It's in the book, unfortunately.
It made me laugh. But I have a question kind of based on that whole idea, because one of the things that you say in your book is that once the event occurs, the state, quote unquote, disappears. And is this what happens to those alternate universes? Like, we get to a position where we're going to make a choice, or there is some potential outcome. Do multiple universes occur for a while and then come back together on the other side of the event?
I don't see how they can come back together. They basically split at the event. It's as if we live in a huge reality that can encompass all those different possibilities happening simultaneously and then evolving into what we would perceive as separate universes. So they, yeah, there was an interesting analogy that, and I'm ditching on the name, that I actually got from a philosopher who had written a paper, and the references are in the book properly, but I'm ditching on the name right now. But you might ask, okay, how many realities are there? Can you count them? But you really can't, because you have to. The universe is filled with quantum mechanical events, and these things are happening all the time. And so at any given moment, if you could freeze time, right, and then proceed right after that quantum mechanical event, you would have just formed two different threads of reality, but they would all be completely identical except for this one little thing that would be different. So their evolution, I mean, there are lots of quantum mechanical events that are happening all the time that don't actually affect your life or my life, right? Some particle is decaying in some star 100 light years away, and it's not going to change our conversation, really. But other things may actually affect us. So a lot of these realities really are, you can think of it more as a continuum, I guess. So the analogy that I came up with based on this guy's thinking was, imagine if you had a bunch of sheets of paper and you sprinkled some ink on all of them, little dabbles of ink, and then you stack them up fairly quickly so that the ink would bleed from sheet to sheet. Then what you would get, but there are a few places where the ink had dried. The little dots were so small they dried. What you would get is within each sheet would look very similar in terms of its dot pattern to the ones above and below it, because of the way the ink would bleed below and above. But each would be very slightly different from the others. But if you thumb through this large stack of paper, when you get an inch away, you would find a pattern of dots that's totally different from the one that was an inch further down. So you could sort of imagine that there are all of these different, it's a continuum of divergent realities that are sort of happening all the time in this strange sort of interpretation of quantum mechanics. It's consistent with what we know in that the mathematics holds together for quantum mechanics, and this is a way of looking at it. There's another way of looking at quantum mechanics that does not involve this idea of sort of the multiple universes, and it's called the Copenhagen interpretation. And there you basically have a universe that encompasses, for every quantum mechanical event, it encompasses, the mathematics encompasses all the possibilities, and then it just collapses to whatever actually happens instantly. And the idea is you don't worry about that instantaneous collapse, because you can't actually measure the mathematics that's giving you those probabilities, which we call wave functions. All you can measure is actually what happens in the end anyway. So this is an entirely different way, and I guess I would argue is a more conventional way of looking at quantum mechanics, and it was really the only interpretation that really had a lot of adherence, I think. Oh, gosh, through most of the last century. I mean, when I was in graduate school many years ago, I don't think we really gave the whole many worlds idea much attention, but it was invented in 1957, which I'm happy to say was long before I was in graduate school. But there have been some other things that have it's a developing area, and so there's been something called decoherence that's been developed, which has worked well with the many worlds theory. So I think it's an area that I dare say maybe gaining adherence in physics. It is fairly conventional in terms of it has this weirdness of the multiple universes, but nobody argues about the formalism. In fact, the formalism is more elegant than the ideas behind the Copenhagen interpretation, I think. So, in a sense, it's theoretically much prettier.
It just seems like if we're creating this new reality, this is where I get hung up. If we're creating, and I'm going to totally minimalize this, hundreds of thousands of new realities per second, because there's got to be gajillion quantum events that are happening in our universe every second, then there'd be more than the deficit of these things like every second.
And that is one of the mind-boggling aspects of this strange way of looking at things. And so because of all these possibilities, I mean, people say anything that could happen has happened within, or happens within this multiverse. And as bothersome as it seems, we can't move from the thread in which we find ourselves to one of those parallel threads. That we don't know how to do. And I think by construction we really can't do that. So
but it also implies that the threads are having threads that are having threads, and it just becomes this geometric. Would that be right?
If you can imagine
progression.
You can imagine we have a universe, and let us imagine that we effectively stop time, so nothing else is happening anywhere except for this one particle that's sitting in front of us that can decay with one of two orientations. And so then this thing decays, and so now we have two absolutely identical possibilities within this overall wave function of the universe, and then we say let time go, and each of these now evolves basically independently. So you start out with universes that are the same, and because each of them now will involve new quantum processes which may decay in different ways in each of them, they will actually diverge, even though they started out with no difference whatsoever except this one single particle. It's pretty bizarre stuff. It really is. So that
but
is,
this
that
is
is
all mathematically based.
Well, it's more
that was
than
a really
that.
stupid
I mean,
question,
it's experimentally driven, right? I mean, we have lots of experiments that support the concepts and the calculations that are borne out from quantum mechanics. I mean, it is a way of looking at the universe that is very well supported by scientific methodology and the scientific method, even though it gives you some pretty strange ideas. So
is what you're saying that like they shoot off a particle in a particle accelerator, and then when it does whatever a particle would do, they end up, instead of with just one particle, they end up with two particles that are showing, and hopefully I'll remember your words correctly, two different decay spins rates. Things.
Yeah, we can certainly do that kind of thing, but what we can calculate in quantum mechanics is if I shot 100 million of those particles, I could tell you exactly how many times I'll measure one orientation and how many times I'll measure the other orientation. And that, when we do the measurements, we find out exactly, we get it to agree exactly with our calculations. What I can't tell you is if you shoot one, whether it'll decay one way or the other way. So to the extent that quantum mechanics can tell you things, it seems to agree with nature very, very well. But it has built within it a certain degree of indeterminism.
Okay. Now you're going to be starting to talk about the observer and their role in the process, and I'm like, let's move along.
You could, yeah. We could go a different direction if you want. We've been talking about the parallel universe idea. There are other ideas that are out there which are more cosmological in nature, that are also well supported in terms of science, I should say, that are inferred from good science. I have to be really careful because none of these multiverses they are not currently scientifically supported directly. I cannot step outside of our universe, either parallel universes or a cosmological universe, and actually measure the fact that we live in multiple universes. What I can do is tell you that the infrastructure that is supported by science basically implies that one of these multiverses exists, and that is the case for both cosmology and in quantum mechanics. So in cosmology, for example, you could imagine there's a limit to the size of the universe that we can actually experience, because space is expanding, and the further away it is from us, the faster it is moving away from us, which may sound sort of strange, but the idea of expanding space you can think of as if you imagine a loaf of raisin bread dough, and you let the dough rise. Two raisins that start out very close to one another in the raisin bread dough will move apart from one another. Two raisins that start further apart from one another in the raisin bread dough will move apart from each other, but they'll move apart faster, and the reason is because there's more dough between them that is actually expanding. So if you extrapolate that idea and you allow the space in the universe to expand, then what you discover is that objects which are further from us in space, so galaxies that are further away, are actually moving away from us faster. And so I've sort of come at this backwards because the observation was made first. Hubble discovered that, in fact, galaxies further away from us are moving away from us faster, and from this infer that the space in the universe is actually expanding. So what that means is that if you ask what part of the great reality we can actually ever experience, there comes if we look further and further away, there comes a point where the space is expanding from us faster than the light can travel, which means there comes a point where light will never come to us from that part of reality. In other words, there's a finite part of the great reality which could possibly be observed from us. So if there is a great reality that is larger than our observable universe, then that would be a multiple universe. That would be a multiverse. And it turns out, oddly enough, that there are very compelling reasons to believe that that's the case. So we see that we live in this expanding universe, and that's basically an experimental fact. I mean, you can try to explain the observations in different ways, but it turns out that the way that most people think about it, we call the hot Big Bang model. So we say that at some point the universe was smaller and hot and dense, and space is expanding, and as it expands, a number of things happen. You can imagine as if you, for example, have, if we start with ice, or if we start with steam and we cool things down, then it will turn to water, and then eventually it will turn to ice. So if we go back in time, it turns out that matter as we see it now really isn't what you would see at the very beginning of the universe. In fact, neutral atoms couldn't hold together in the early stages of the universe. The nuclei and the electrons would be blown apart by high-energy photons and everything every time they would try to come together. So the universe was actually very different, and it was different in ways that we can actually understand, because we can reach these energies in the lab up to very, very early in the universe. We can actually understand the physical processes of what would have happened as the universe expanded and cooled. And there are a number of things that you can actually predict.
Steve.
Uh-oh.
Steve.
You're going to pull me back down to earth here, huh?
No, I want to keep on this topic, but we need to go to break.
Oh, boy, time flies. Doesn't time fly? Oh, my goodness.
No, it does. But when we come back, let's talk more about the Big Bang, because I have a question about it, especially that 13.7 billion year date, because I have issues. Anyway.
Okay.
All right. So
Sounds
when we
good.
come back, we'll be talking with Steve Manley. His book is Visions of the Multiverse, and we'll be back after these words from our sponsors.
Just Energy Radio with your host, Dr. Rita Louise, will return right after these messages. back to Just Energy Radio with Dr. Rita Louise.
Hello and welcome back to Just Energy Radio. I'm Dr. Rita Louise, and thank you all for staying tuned. Steve, before the break, Steve's book, Visions of a Multiverse, Science and Physics that you maybe could even understand, even though it has the half-dead cat in it. Anyway, sorry. I really get hung up about that cat. Anyway, we were talking about the Big Bang.
We could use a dog if you're a cat lover. Would that help?
Well, no, it's the half-dead part. You put it in a box, you put poison gas in there. It's like, come on. Anybody that has even a 3-year-old would figure out dead kitty.
Well,
and I'm not
blame
even
it
a
on
rocket scientist or
Schrodinger.
anything. Well, no, I'm not blaming it on you. I'm just... Anyway. You were talking about the Big Bang. Mm-hmm. One of the things that I have a little bit of an issue with, and maybe you can incorporate this, I was trying to, during the break, try to figure out how to make this be a question and a comment at the same time, but it wasn't working. They say that the universe is 13.7 billion years old. Then, and it comes across as, boom, the universe is 13.7 billion years old, like it's a fact. But then I was doing some research and discovered that that is only how far we can see out into the universe, period, and has really nothing to do with the real age of the universe. True? And so
yeah,
I guess my question is,
let me talk about this in 2 stages, all right?
Okay.
Because one stage is if you take what we see now in terms of the size and the way matter is distributed in our universe, and we take the speed with which everything is receding, that is the speed with which the rate at which space is expanding, then you can extrapolate backwards in a fairly straightforward way, right? If you're watching a ball blow up, and if it were blowing up at a constant rate, you could basically extrapolate that back in time to the point where the ball is a point. And so we can do that with our universe effectively and come up with a time that is the beginning of the universe. And of course, it's not a fact. It's an experimental sort of thing that is a number that's changed through the years as people have made better measurements. It's also gotten a little more complicated because there's more to it than just the fact that the space is expanding and gravity is trying to slow things down. There are other things at work. For example, we have discovered, in fact, that the rate of expansion of the space in the universe is increasing with time, which is something that we can put in our equations with a certain term that has units of energy. So we call this phenomenon dark energy, but we don't actually know what it is. So if we give a date, I say we, I don't actually do this particular type of science. I do more particle physics, but my colleagues will give you a date. They're having to make assumptions about how the expansion rate of the universe has changed with time. And I think the sense I have, but I've not made a study of it, is that 13.7 billion year number has been fairly robust recently. So now, that would be stage one. So if you could imagine all that we see being basically all that there is, and we extrapolate back in time to where the density becomes infinite, basically, or you get to a point, then that would be the start of our universe. And I think that's more or less what people mean by the 13.7 billion years. But let me talk for a moment and then come back to that. So we believe in the Big Bang in part because we see the space seems to be expanding, and because there are things you get, if you believe in this idea of the Big Bang, that the universe is once hotter and denser, we can actually project what the matter would have done at the time and what it would look like now. So, for example, at the very earliest stages of the Big Bang, it was so hot and dense that light nuclei couldn't even exist. In fact, protons and things that make up the nuclei couldn't exist. And as it cooled and expanded a little bit, these things would have condensed out, basically. And we know enough nuclear physics to be able to model how these nuclei would have been formed, and we can predict, for example, the ratio of different types of light nuclei that we should see in intergalactic space. And lo and behold, people go and they look, and they find ratios that are exactly like what you would believe if the Big Bang were true. Similarly, there's a stage where the universe is opaque to light before neutral atoms could be formed. And when neutral atoms were formed at about 400,000 years after the Big Bang, the universe became transparent. And the light that was bouncing around in the universe at that time, not able to go very far because it would continuously be absorbed or scattered, all of a sudden the universe became transparent, and that light could travel forever. And we can actually see that light now from very far distances away from us. We call it the cosmic microwave background, and it fits exactly the characteristics you would expect for the Big Bang. So there are lots of pieces of observed, complicated things that agree very well with the Big Bang model. So it's a believable thing in the end, scientifically. Then the problem is, if you were to believe in the Big Bang by itself, it turns out there are a number of actual big problems that get created. One of which is physics as we know it breaks down when things reach infinite density. So if you truly extrapolate back till everything is a point, we don't have science that, and we don't know what happens, right? We don't really have stuff that models that very well. So that's one little problem. But perhaps even a bigger problem is that this cosmic microwave background, radiation from the early stages of the Big Bang, this light, we actually see it coming at us from all different directions. And it's coming at us, basically it has the same color, which is a way of saying that it was emitted by material at exactly the same temperature. So if I look at light straight up, and if I were able to look through the Earth and look at the light coming at us from the direction of China, it's coming at us, it was emitted at the same temperature. Yet the part of the universe that I'm looking at straight up and the part of the universe I would be looking at if I went straight down, those two pieces of the universe where that light was emitted have never been in causal contact with one another. How do they know what temperature to be at? So in the Big Bang theory in and of itself, it turns out, and these are just two, there are a number of other little problems that aren't really so little. There are some very big basic problems with the Big Bang model in and of itself. So the way that people have conventionally solved this is a pretty wacky idea. And there were a number of people who worked on it, but the guy who gets most of the credit, I think, would be a fellow named Alan Guth at MIT. He's still alive and kicking at MIT, and he pushed this in I think it was early 80s. It's an idea called inflation. So the idea with inflation is that somehow what became our universe started out very, very tiny. And you can theoretically create, mathematically, you can create conditions in space, in mathematics we call quantum field theory, such that it's unstable and will expand really fast. And when I say really fast, I mean superluminally, really, really fast. And so if you imagine that the universe started out very, very tiny so that everything was in causal contact with everything else, but then was unstable and expanded really, really super fast so that it became vastly larger than our observable universe at that moment, and then slowed down to where you have an expansion rate similar to what we have, and the energy of that expansion got sort of thrown into particles and light in the early stages of the universe, you can actually create a model for a Big Bang which doesn't have all these various problems. And this is called the inflationary hot Big Bang model of the origin of the universe, and it is the paradigm. It is the given model that basically is what people, I don't want to say believe in, because science isn't about truth, but it's the model that people would vote for as most being supported by the evidence these days, typically. And so the thing is, if you have this weirdness called inflation, so if you had something small that began to do this superluminal expansion, they don't know how to stop it except in small areas. So a way to think about it is the space is expanding, and in certain places, the characteristics of that space will fluctuate a little bit because of quantum mechanical processes. And when that happens, in those little places, you might locally create a form of space that doesn't expand so fast, that it slows down. And each of those points might be what we would consider, what would look to us like the formation of a Big Bang. So in this weird theory, you end up with this super expanding matrix, whereas here and there you'll get these sort of bubble universes formed, which might have somewhat different physics because the fluctuations in the nature of the space that creates the slowness and everything actually also can make the physical constants vary. So the laws of physics could be a little bit different in each of these bubbles. And so to come back to your initial question about the 13.7 billion years, if we were to define our universe as all that we can see and extrapolate back in time and sort of in a sense, time begins at the point where we would reach that infinite density. But if you believe in inflation, I don't know when inflation may have started, but you could have this expanding matrix, and our Big Bang might have just been the formation of one bubble in this continually, eternally inflating matrix. And you even have to, you sort of would have to even get a different idea of time, because in a sense, you would have to be able to step outside of our universe and have sort of a time that is somehow associated with the inflating matrix, so in a sense, I think that's the answer that may have gotten you, what may have been confusing, because there are pictures where there is a reality that is much larger than the reality that we experience as our universe. And so depending on which time you're talking about, you might have been around for an infinite amount of time, or you might have just been around for 13.7 billion years.
Yeah. What about black holes? There are some people that say that the Big Bang occurred because the matter from a different universe got swooshed through a black hole, white hole, tubey thing to create our universe as we see it today.
Yeah, I'm not sure about the white hole terminology, but there is one multiverse, and so just so your listeners have a picture, the book that I've written covers about 11 different types of multiverses, and some of them are really quite independent of others, and some of them have some associations, and they all could, in principle, be true at once, in a sense. So it may not be a question of whether we live in a multiverse, but it could be how many different types of multiverses do we live in. So we've talked about quantum mechanical ones. We've talked about a cosmological version, of which there are some others. There is another idea, which you're bringing up, which is by a guy named Lee Smolin, which is a fascinating and strange idea. Imagine that you have a black hole forming, and so the space inside that black hole will collapse. From outside the black hole, what we would see is that as the space collapses, eventually the gravitational field becomes so strong that light cannot emit. So basically you get the formation of this region in space where the gravitational field is so strong that we can no longer get a signal from it. So it becomes isolated from our universe in that sense. if you now calculate or think about what happens inside the black hole, you could imagine that the matter continues to collapse because it's feeling the gravity, so there's nothing to stop it from collapsing to a point, really. Now, our understanding of gravitation breaks down at a certain stage. It's sort of well understood at what point that it is where our equations don't quite make sense anymore. And one needs to invent something which is called quantum gravity in order to truly understand this. Lee Smolin is a guy who works in these type of area. He works in something called, I think, quantum loop gravity or something. But he has speculated. As far as I know, we don't have an accepted, really working theory of quantum gravity. But he has speculated what might happen when the matter collapses toward a point. And one of the things that could happen is that basically you get a bounce, that the space-time, instead of collapsing, begins to expand. Now, this is happening inside the black hole, so we would never see it if it were happening in our universe. But inside the black hole, you could create conditions for the space to bounce and actually begin to expand. In other words, you could basically have an expanding universe born inside that black hole, which more or less I think is what you were just saying. And he had there's a funny idea about this, is because the physical constants are associated with the very nature of the space itself, and this idea, at least is the way that I think about it, is something that comes out of string theory, and I probably don't want to get into that right now because we're running short on time. But basically the idea is that there are many dimensions. We only perceive 4, and there are ways to sort of fold up and compactify those extra dimensions so that we don't perceive them. But when you do that, it turns out how you compactify all those different dimensions can determine physical constants and sort of the laws of physics that we perceive. So what happens is if you have small quantum changes in how those extra dimensions are folded about, you actually are also making small changes in the physical constants of that universe. So what he claims is that the space collapses in upon itself and then bounces, and as it comes out, because of you've had some quantum interactions in there, the space that's expanding might be slightly different from the space that was collapsing in, which means the physical constants of the universe that's being born within the black hole could be a little bit different from the physical constants of the universe that created it. So this gives you a funky sort of type of evolution. So just like if you have small changes or even occasionally abrupt changes in the characteristics of a population of animals, sometimes you get a change which is beneficial to the survivability, and I guess this is sort of the idea of how evolution creates weird sort of new beasts. And so his idea is that you have cosmological natural selection, that if we have a universe that is that has the physical constants such that it's more prone to create black holes, and there are certain conditions, we could imagine having physical constants like gravity being much stronger, or the nature of the mass of the neutron and the proton being different, so that fusion wouldn't work inside of stars, so that stars wouldn't really form. There are lots of ways in which you could imagine having a universe where things might not work to create black holes. But if you had a universe that created a lot of black holes, it would beget within those black holes universes that would have characteristics similar to it, so they would create black holes. So the idea is you could have an infinite number of possible universes in terms of physical constants being created perhaps in this inflating matrix of which our universe is only one of an infinite number. And in some of them, I mean, you could imagine having the physical constants take all possible values in these infinite number of different universes, and in some of them they'll be ideal for black hole production, and in those you will have universes formed within those black holes that will actually also be optimal for black hole production. So he has this weird idea. He says, because scientists don't like our universe to be unusual in this picture, it means that the vast majority of universes that are out there should be pretty optimal for black hole production. So he argues that we should be able to make all the measurements of our universe, and if we truly understood what was behind making black holes, we would find our universe to be optimal for black hole production. And this is an example of something that we can actually do experimentally, because if we found that, in fact, our universe was not optimal for black hole production, it would basically scientifically disprove his hypothesis. It would say there's something wrong with Smolin's picture. And he holds this up as one of the few, or if not the only, multiverse idea which is actually scientifically, or which you can really call hard science. Because a lot of these ideas, although they may be based on things that have experimental support, we can't actually falsify them. So,
I wonder how come people believe physicists, but they don't believe ghost hunters or psychics or anything
well,
of that nature.
Yeah, I mean, I think that it has a lot to do with the reproducibility and the methodology. I mean, the truth is, the hot Big Bang model with inflation behind it has a tremendous number of very complicated measurements that are made which support it. And it's sort of like this large network. There are nuclear physics measurements, there are measurements of light coming from galaxies, and on and on and on. And you can't just have some idea throw out there and have it be consistent with all the data. So these things evolve with time, and they are married to experimental things. But at any given time, if you go to the cutting edge of ideas, like the multiverse, you find yourself in a region where, you're sort of making things up, but you're not making it up out of a vacuum. And so I think part of the problem with UFOs, for example, I have seen something I didn't understand. I had an uncle who was a G2 officer to Patton who saw something before things were flying, actually, and when he was young in the Valley of Virginia, that he described to me that would be a classic UFO encounter. And this guy wasn't a fruitcake. I mean, he was a colonel in the U.S. Army and very respectable guy that I knew that was hardly going off on strange things. So there are weird things out there, but the problem is scientific methodology requires that it be reproducible, that it be something that we can actually make quantifiable measurements on. But until you can create such a situation, it's hard to sort of put it in the realm of scientific models and things like that. So if somebody comes in and says to me, I saw a ghost yesterday, I think, well, that's interesting, tell me all about it. But unless I can go and see that ghost or make measurements of that ghost in some reproducible way, I don't know what to say about that as a scientist, right? I may or may not choose to believe this person, but it becomes a matter of opinion.
Mm-hmm.
Whereas
well,
with the Big Bang, we all get together in a room, and there is some room for opinion. I mean, it's not that scientists don't have opinions, and it's not that you don't have aesthetic sense in development of these models, but there are very strict rules to how the methodology works and when you don't sort of overthrow the paradigm. And we're not always right? I mean, we thought that the Earth was the center of the universe at one point, and then we thought the sun was the center of the universe at one point, and gosh, now we're finding we may not even be a unique universe. The Copernican revolution may be living on. We may have actually reached the ultimate stage.
That's
so
pretty
I think
fun.
Not all opinions are equal in a sense. Scientific methodology has been incredibly successful. Is it the only way to think about the universe? Well, many scientists might say that, but no, of course not. I mean, religion is a way of looking at and trying to understand the universe. It just has a very different methodology. So I think you just have to bear that in mind in a sense.
Hey, Steve. It's time.
Sounds like we're out of time.
So we need to wrap up. Let's see. Your book, I'm assuming bookstores around the country, Amazon.com, Barnes & Noble, et cetera, et cetera.
You got it. Hopefully you can find it. Certainly it's online, no question of that. I've certainly seen them in Barnes & Nobles and Borders and stuff like that. So it's around. Buy
cool.
12. I would love to sell more.
You heard the man. Buy 1 million.
That's right. Buy one for each multiverse in the book.
Yeah. All right. I know the music's going to come up really, really fast here. If you had to pick one of the multiverse theories that either we've talked about or haven't talked about, which one do you gravitate to?
Ooh, wow, you're going to make me vote? Well, I have to say that the cosmological ones, the fact that I think the reality out there is larger than the universe in which we can observe, I don't think that's even all that contentious. So that's my leading one to believe in.
Cool. I mean, there's reporting stuff, and then there's what your heart tells you, which can be two totally different things.
Well, there's room for that here. There's no question about it, because you're not going to be able to step out there and prove it.
Right. Steve, thanks so much for coming on the show and sharing your insights about multiverses and making it be where my head didn't spin too much. So that was really good.
My pleasure.
Okay.
Great fun.
All right. Thanks, Steve.
All right. Thanks, Dr. Rita. Have a good one.
Thank you. That's Steve Manley. His book is Visions of a Multiverse. And next week, speaking about ghosts a little bit earlier, we're going to be speaking with David Roundtree about the science of ghost hunting. Woohoo! Anyway, till next time, Dr. Rita Louise, be blessed.
Join host Dr. Rita Louise each week at this time for Just Energy Radio. Point your browser to www.justenergyradio.com for more show information and to contact Dr. Rita. Until next